All right, we all know transistors are, the bedrock of modern electronics. But how do you get one to do more than just switch on and off? How do we turn it into something that can actually boost a signal, like for your headphones or a radio? Well, that's exactly what we're jumping into today, the art of taming the transistor and really making it work for us. This is where the magic really starts, turning that raw component into a practical, powerful amplifier.
And hey, don't just take my word for how important this is. One of the classic textbooks in the field literally calls this stuff the heart of a first course in electronics. So why the big deal? Because these principles we're about to unpack apply to pretty much every kind of transistor you're ever going to use. You get this down, and you've basically unlocked one of the most fundamental skills in all of electronics.
So what's the big challenge here? Well, it all boils down to this really interesting paradox. For a good, clean amplification, we need our amplifier to be perfectly linear. The problem? The very devices we use to build them are, well, they're anything but.
And that's the absolute core of the problem. A transistor just doesn't behave like a simple, predictable volume knob. The relationship between the signal you put in and the signal you get out isn't a straight line, it's a curve. So if you just blindly feed your signal into it, you're not going to get a bigger, cleaner version. Nope, you're going to get a distorted mess.
This really paints the picture, doesn't it? Over on the left, that's the dream, a perfect magnified copy of our input signal. But on the right, that's what happens if we're not careful. The signal gets clipped, warped, and distorted because the transistor is being pushed into those messy, nonlinear parts of its curve. So, the million-dollar question is, how do we get from that ugly reality to the clean, perfect ideal?
Well, the solution is actually incredibly elegant, and it's a two-step process. The trick is to separate the work into two totally distinct jobs, a DC job and an AC job.
Okay, so first up is the DC job. Think of this as setting the stage. We use a steady DC voltage to park the transistor right in its sweet spot, a state where it's perfectly prepped and ready to amplify. Then, and only then, comes the AC job. We take our small input signal, the one we actually want to amplify, and we let it ride on top of that DC level. By keeping that signal small, we're basically just using a tiny, almost straight piece of the transistor's big curve. It's a brilliant trick to make a nonlinear device behave like a linear one. Now, this sweet spot has a proper name. It's called the Q point, which stands for quiescent point. You can think of it as the transistor's idle state. It's not off, and it's not slammed on either. It's just sitting there, perfectly balanced in the middle, ready to react to our small AC signal without getting shoved into those extreme, distorted zones. And to put it in more technical terms, this whole process of DC biasing is about parking the transistor in its prime real estate. For a MOSFET, that ideal zone is called the saturation region. For a BJT, it's the active mode. In these specific zones, the transistor acts like a well-behaved, predictable, controlled source, which is exactly what we need for a clean amplifier. Okay, so the DC job is done. We've set our stable Q point. Now what? How do we actually analyze the AC part of this? How do we figure out how much gain we're going to get for that small signal? Well, this is where we pull another powerful tool out of the engineering toolkit.
This is where the real genius of the whole approach shines through. Because our AC signal is so small, we can effectively zoom way in on that Q point and just pretend that that tiny little segment of the transistor's curve is a perfectly straight line. This simplification is unbelievably powerful. It means we can forget about all the complex DC biasing for a minute and use a much simpler linear model to analyze just the AC signal.
And when it comes to models, we've got a couple of go-to options, the hybrid pi model and the T model. Honestly, they're just two different ways of looking at the exact same behavior. The hybrid pi is kind of the general-purpose workhorse model. The T model, on the other hand, becomes super handy for analyzing certain kinds of circuits. It's like having two different wrenches in your toolbox. You just grab the one that's right for the job at hand.
So what makes these models tick? They're really defined by just a few key parameters. The big one, the star of the show, is transconductance, or GM. Just think of that as the raw amplification power of the transistor, how much output current you get for your input voltage. Then you've got things like input and output resistance, which help us model how the transistor interacts with the rest of the circuit and account for the fact that these things aren't perfect in the real world.
All right, we have our strategy, we have our analysis tools. Now it's time to actually build something. It turns out there are three fundamental ways to wire up a single transistor amplifier, and you can really think of these as your basic engineering Lego blocks.
And this table here is your cheat sheet. The common source or common emitter configuration, that's your go-to when you just want a ton of voltage gain. The common gate or common base, That's really useful in other specific situations, especially with low impedance sources. And finally, the follower. Its gain is only about 1, but it's an amazing buffer, kind of like a universal adapter for connecting different circuit stages together without messing them up. Each one has its own unique personality and use case.
Now here's a really cool trick that engineers use all the time. Sometimes you can actually add a resistor to intentionally reduce the amplifier's gain. And you might ask, why on earth would we want less gain? Well, it's a trade-off. In exchange for giving up a little bit of that raw amplification, we get an amplifier that's way more stable, more linear, and less sensitive to things like temperature changes. It's a classic engineering trade-off, sacrificing one thing to get something better in return.
So, let's just pull this all together. We started with this fundamental problem, the transistor's nonlinearity. Then we saw this elegant two-step solution. Set the DC bias point, then analyze the small AC signal. And finally, we looked at the 3 basic Lego blocks we can build with. This right here, this is the complete framework you need to start designing real-world amplifiers.
And if you take just one thing away today, let it be this. This entire framework, this whole way of thinking, it works for both MOSFETs and BJTs. It is a unified, universal language for designing amplifiers. Once you get these principles, you can apply them to a massive range of circuits, no matter which type of transistor you're holding in your hand.
So, as we wrap up, I want to leave you with a designer's question. You've now got the fundamental tools, you know that you can't have it all, it's always a game of trade-offs, so the next time you sit down to design a circuit, what are you going to prioritize? Are you going for maximum possible gain, rock-solid stability, or crystal-clear linearity? The choice and the trade-off is up to you.